Okay, so in the last section here of chapter 12, we're going to be taking a look at some of the main reactions of alcohols, and then also by extension aldehydes and ketones as well. And we're going to see, why we had first of all talked about identifying an alcohol as being primary, secondary, or tertiary in the first place. Before we get to that, though, let's take a look at a thing that we're going to see quite commonly in organic chemistry, which is we're going to see a reaction that is going to be the opposite or the reverse of a reaction that we saw previously. And this here, the first one, is the dehydration of alcohols, right? So if you recall, for reference, right, we talked about a reaction that sounded similar to dehydration, which was hydration reactions before, and specifically we saw the hydration of alkenes back in chapter 11, right? And if you remember, we saw that alkenes could be hydrated, right, which meant that we added H2O to produce an alcohol, right? So now what we're saying is, if we have an alcohol, we could do the opposite to it. We could dehydrate it, which means that we're going to remove water. And again, when we added water to an alkene, we thought of it as a H connected to OH. Similarly, when we remove or dehydrate an alcohol, we're going to remove H2O as an H and an OH. And this dehydration reaction will happen under conditions of heat, and we're also going to need an acid catalyst, typically represented by an H+. Remember, a catalyst is something that speeds up the reaction. Right, so we're going to lose water. We're going to lose an H from one carbon and an OH from an adjacent carbon atom. And as a result, what we're going to produce is an alkene, and we're going to get water. All right, so let's think about that for a second. We saw hydration, where we had an alkene plus water to make an alcohol, right? And now we're saying in a dehydration, we're going to take an alcohol and we're going to remove water from it. We're going to make an alkene and remove the water, right? So these two are essentially opposite processes. And that's very common in organic chemistry. By changing the conditions, we can force a reaction to go in one direction versus another. All right, so let's take a look at an example. We have here our alcohol. In this case, it is ethanol, a 2-carbon alcohol. And our conditions here are acid, H+, and we have heat. We're going to lose an OH from that carbon, and we're going to lose an H from an adjacent carbon, right? So we take these two things away, we remove it as our H2O, and now we end up with each of these carbons here having just 3 bonds. In order to make those carbons happy, we're going to make now a double bond between those two things, which is the corresponding alkene. In this case, it is ethene that we end up making. Right? If we take a look at another example where this can happen, let's say we had a cyclic alcohol, something like this, and we subjected it to the same conditions. We have heat and we have H+. right? You have to recognize those conditions as dehydration conditions, or conditions for this particular reaction. We're going to lose an OH from, well, that's the only place we can lose the OH from. And then don't forget that you have two H's on each of these carbons on your cyclohexanol. Right, so we can lose that OH from that carbon. And we also have another H attached here. And we lose an H from an adjacent carbon, right? So either from this carbon here or the carbon underneath, let's just choose the one on the bottom, we lose that H. So we lose water in the form of an H from an adjacent carbon and the OH from the carbon where the hydroxyl is attached. So if we were to draw the corresponding product, all right, we end up now taking these two things away. Now we have to introduce a double bond right here to make sure that carbon is satisfied with 4 bonds to it. And we lose our H2O as the byproduct, right? That's of a dehydration reaction. Our product here, our main product in question, would be our cyclohexene. So we end up making an alkene when we dehydrate an alcohol, right? I could have just as easily have lost the H from the hydrogen or from the carbon above, right? In which case my structure would look like that. Well, these two things are actually the same. All right, so it doesn't matter where you lose that H from. All right, so dehydration is a very important reaction that the alcohols are going to undergo. The second type of a reaction that they're going to undergo is called an oxidation, and the flip side of oxidation, which is called reduction. So there are several things that we can look at in organic chemistry that tell us whether oxidation has happened. All right, so oxidation can mean several things. And from the name, right, you can probably guess it means adding oxygen or increasing the number of bonds to O. And it can also mean removing hydrogen, right? And we can see maybe all of those things or maybe just one thing when something undergoes oxidation. Reduction is just the opposite of this. So reduction then would mean removing oxygen instead of adding O. It can mean decreasing the number of bonds to oxygen, and reduction can also mean adding hydrogen, right? So they're opposite processes. The thing you want to keep in mind about oxidation and reduction is that they must happen simultaneously. In other words, if something is losing hydrogen, if it's being oxidized, something else has to pick up those hydrogens, something else needs to be reduced. So in other words, if something is being oxidized, something else must be reduced, right? So they go hand in hand. And again, this kind of goes along with the law of conservation of matter, right? So if something is giving up hydrogen, if it's being oxidized, something else has to pick those hydrogens up. The hydrogens don't just disappear. So when it comes to oxidation specifically, the type of alcohol that we're going to be dealing with will dictate what can actually happen. So we're going to first of all take a look at oxidation of primary alcohols. And when your primary alcohols undergo oxidation, they do it in a two-step process. Your primary alcohols are first of all oxidized to produce aldehydes, right? So for example, if you have something like ethanol, right, which we know is a primary alcohol now, that can undergo oxidation to make the corresponding aldehyde, which in this case is ethanol, right? What's occurring or what's happening here? Well, there are a couple of things we can look at. First of all, we go from this type of a bond, a C to an OH, to a C to a double bond O. So we've increased the number of bonds to oxygen, but what you've also seen is we've actually lost hydrogen, right? So we've increased the number of bonds to O, and we've also lost H. Right, so that would be, both of those would mean that the original molecule, the primary alcohol, has been oxidized. That aldehyde that ends up being produced can be further oxidized to make a carboxylic acid. Right, so here we have our ethanol from the previous step, and we can kind of chart to see how it changes. So we have a C with 2 bonds to an O. How it changes now is we've increased the number of bonds to oxygen now to 3 bonds to O, right? So here we've increased the number of bonds to oxygen. We've made the corresponding carboxylic acid. We'll look specifically at naming carboxylic acids in the next couple chapters, but just to kind of let you know, we end up making a carboxylic acid known as ethanoic acid, right? So all we've done is we've changed this part of the molecule from an alcohol to an aldehyde, and from an aldehyde to a carboxylic acid. The remaining part of the molecule doesn't change, right? So that stays the same, in other words. So the reactive part of the molecule is the part that actually we want to focus on. So let's take a look at another example here really quick. So if I had an alcohol that looked like this, right, it may look kind of big and cumbersome, but really all you're focusing on is this region of it. So if we oxidize it, right, first of all, we're going to get the same number of carbons, 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. And now we're going to change that alcohol to an aldehyde. Right, that's all I'm changing. And then if I oxidize this even further, right, I'm still going to have my 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. I'm just going to change the aldehyde now to a carboxylic acid. And that's it. That's all you're doing when you oxidize a primary alcohol. Secondary alcohols, on the other hand, they get oxidized not to produce an aldehyde, but to produce a ketone. All right, so if we have here a secondary alcohol, something like 2-propanol, right, what we end up doing is we oxidize it, and the shortcut for representing oxidation is an O in square brackets, right? So that means oxidation whenever you see it. So if we go back to our example here, we can say O in square brackets, right? That means oxidation. So when you oxidize a secondary alcohol, what we end up doing again is we increase the number of bonds to oxygen from 1 to 2, but we've also lost a couple H's as well. All right, we lost an H from here, and we lost an H down at the bottom. So we oxidize a secondary alcohol to make the corresponding ketone. We end up making propanone in this case, and then the ketone cannot be oxidized any further. Right, so the oxidation of a secondary alcohol stops at the ketone. Tertiary alcohols, they do not undergo oxidation, right? So if you try to oxidize it, no product, or we say no reaction occurs, and that's because there isn't any hydrogens attached to the tertiary alcohol carbon there for it to be lost directly. All right, so let's take a look at a couple examples of where this can happen. We looked at the oxidation of ethanol previously. So ethanol can be oxidized to the corresponding aldehyde first, which is ethanol, and then this can be oxidized again in several steps, eventually to produce carbon dioxide and water vapor down the road. And we actually take advantage of this oxidation process in the body in the use of these breathalyzers, right, which actually are able to detect the alcohol content on a person. If we take a look at the oxidation of our thiols, remember the thiols are things that contain the sulfhydryl group, the SH. Right, and when these undergo oxidation, we're going to be looking specifically at the loss of hydrogens. And what occurs is we end up connecting, so two thiols can combine to produce what's known as a disulfide bond or a disulfide bridge, as those H's are lost and as the sulfur then combines with the other sulfur that's right next to it. All right, so here we can see an example of where this occurs, and really where this happens a lot is in proteins, right? A lot of times in your hair, for instance, what keeps your hair in a particular shape are the disulfide bonds that you find in the hair proteins. And when you get your hair, curled or straightened or whatever, or styled, that's what you're actually doing. You're breaking these disulfide bonds, and then you're reforming them in a brand new shape. All right, so here we can see where these thiols actually start from. So there's a thiol on the left side and a thiol on the right. And what can happen is under the right conditions, these can be oxidized, and these two H's end up being lost. And then the sulfurs that end up being by themselves, they just connect with each other here by this disulfide bridge, or that disulfide bond, right? Disulfide there meaning two sulfurs that are attached to each other, and it ends up bringing those two molecules together by that covalent bond, right? That ends up being formed. And there are some tests that are done in the lab to distinguish or to differentiate between certain types of aldehydes as well as ketones. Right, one of the more common tests that you'll see in your textbook, and if you were to do the lab, if you had to do the lab, in person, this is a very common test. It's called a Tollens test, and this Tollens test invokes the use of Tollens reagent, which contains a silver ion. And this works in the presence of aldehydes, right? So it actually is positive for aldehydes. It's a positive test for aldehydes and not, or it's negative for ketones. And that's because the aldehydes can be oxidized, but the ketones cannot under these conditions, right? And as a result, if the aldehydes can be oxidized, that means something else can be reduced. So we're taking advantage of the fact of what we mentioned at the beginning here. If the aldehyde is being oxidized, which it can be, something else must be reduced. And what's being reduced in this case is the silver ion that ends up becoming reduced to silver metal. Right? And what's characteristic about this test is that you actually do end up forming, for a positive test, you see silver being produced, and it looks like a silver mirror. So it's sometimes called a silver mirror test for aldehydes. Right? So because the silver here is becoming reduced, right, we say that it's testing for the ability of the aldehyde to be oxidized in the first place. So if we take a look at an example, there's our aldehyde ethanol, Tollens reagent under the oxidizing conditions. The Tollens reagent, the silver ion gets reduced to the silver mirror, whereas the aldehyde gets oxidized to the corresponding carboxylic acid. Right, so you have both oxidation and reduction happening simultaneously, and we actually do see that silver mirror. It's actually quite distinct, and it's pretty obvious. It's kind of hard to mistake the positive silver mirror test. So it works with, and it's positive for aldehydes because aldehydes can be oxidized, but it's negative for ketones because ketones cannot be oxidized. Another test that you'll see, especially in carbohydrate chemistry, and you probably, if you've taken some biology classes, you probably have done this test already, and it's called Benedict's test, which invokes the use of Benedict's reagent. The Benedict reagent contains the copper 2+ ion in it, which is blue. Right, and what this tests for specifically is for the presence of aldehydes that have a hydroxyl group right next to it. Right, so the Benedict solution contains copper 2+ in the form of copper sulfate, copper 2 sulfate, which is, I should probably write that in blue. And then if we have an aldehyde that is close to an OH group, right, that's going to give you a positive test, and that blue color, right, gets converted to a brick red solid, which we call a precipitate. And it's pretty obvious when that happens because you see that color change happen right away, right? And that's due to the copper 2+ becoming reduced to copper oxide, copper 1 oxide, and the aldehyde group here becoming oxidized to the corresponding carboxylic acid, right? So a positive test would, you would be able to see that blue color changing to a brick red color. That tells you that you have an aldehyde that's close to a hydroxyl group, aldehyde close to a hydroxyl group right next door. And the test is negative, meaning you're not going to see that color change if you just have a simple aldehyde or a ketone, right? The Benedict's test is used quite frequently in carbohydrate chemistry to test for what are known as reducing sugars, right? And here you can see the pretty stark contrast that happens if there is a positive test. Right, you start off with a blue color, that's the copper 2 sulfate, that's the Benedict reagent. And then if we have that aldehyde right next to a hydroxyl group, that aldehyde gets oxidized to a carboxylic acid, and the copper 2 plus gets reduced to the copper 1 plus, which is that brick red color. So blue changes to brick red if there's a positive test. So we've seen how alcohols can be oxidized, primary alcohols oxidized to aldehydes, then to carboxylic acids. We've seen secondary alcohols can be oxidized to ketones. Tertiary alcohols are not oxidized. And we looked at a couple tests that we can use to differentiate between them. The aldehydes and ketones themselves can be reduced to the corresponding alcohols, and the conditions that are used here are typically hydrogen. That's you add hydrogen to something. Remember, that's a definition of what reduction is. Or sometimes you'll see a slightly different reagent, sodium borohydride, NaBH4. All right, so in a reduction, we're going to reduce the number of carbon-oxygen bonds, and that can result by simply adding hydrogen or by losing oxygen. These reduction reactions are catalyzed by metal catalysts such as nickel, platinum, PT, or palladium, PD, in order to add the hydrogen to the carbonyl group. All right, so when we reduce our aldehydes, we end up making primary alcohols. When we reduce our ketones, we end up making secondary alcohols, right? So let's revisit what we saw originally. We saw that primary alcohols could be oxidized to aldehydes, which could then be oxidized to carboxylic acids. What we're saying now is your aldehydes can be reduced. Sometimes for reduction you'll see hydrogen in square brackets or R. These can be reduced back to the corresponding primary alcohol. We also saw that secondary alcohols could be oxidized to ketones. And what we're saying now is that ketones could be reduced. Right, the shortcut for writing reduction is hydrogen in square brackets, or R for reduction in square brackets. Ketones can be reduced back to the corresponding secondary alcohol, right? So I mentioned this at the beginning in organic chemistry, right? By changing the conditions, you can force a reaction to go in one direction versus another. So primary alcohols can be oxidized to aldehydes. Aldehydes can be reduced back to the primary alcohol. Secondary alcohols can be oxidized to ketones. Ketones can be reduced back to the secondary alcohols. Right, so if we take a look here at a couple examples, right, here we have an aldehyde, right, which is propanal. We can reduce it, so using hydrogen and platinum catalyst, that tells you that it's reduction. We can reduce it back to the primary alcohol, and we just simply convert the aldehyde functional group back into a primary alcohol. Similarly, if we have a ketone, right, under the right conditions for reduction, hydrogen and a catalyst, we simply convert the carbonyl back into the alcohol, which in this case is going to be a secondary alcohol. Right, so it's just the opposite of oxidation of the alcohol. All right, so let's take a look at some examples of where we can apply that information. We went through a lot of reactions, what seems like a lot of reactions in this subsection. So let's practice a couple things here. So it says select the product for the oxidation of the following. So we have this thing, and remember that means oxidation. All right, so this is an alcohol. The presence of the hydroxyl group tells you that. What type of alcohol is it? Well, we look at the carbon that's directly connected to the OH, and it itself is connected to 2 other carbons. So that would make it a secondary alcohol. Right? Secondary alcohols are oxidized to ketones. Right? So all we need to do is to convert this into a ketone. The ketone has the carbonyl connected to carbons on either side. Right? These parts of the molecule here are not going to change. So we have a CH3 on the left side, we have a CH2 and a CH3 on the right. Right? So that'll be our corresponding ketone that we get when we oxidize a secondary alcohol, and that would be our option B down here. All right, so it says select the product when this thing undergoes the following reactions, right? So we have it, first of all, we're going to oxidize it initially. So again, this is an alcohol, right? The OH is attached to this carbon, and this carbon is itself directly attached to one of the carbons, so that makes it a primary alcohol. Primary alcohols are oxidized first to the aldehyde, and then if you keep oxidizing it, right, we make it the corresponding carboxylic acid, right? And really the only part of the molecule that is going to change is the part where the OH is attached. So we have a 1, 2, 3 carbon, 1, 2, 3 carbon alcohol. We're going to oxidize it. We're going to change this hydroxyl group to an aldehyde. So we have 3 carbons, 1, 2, 3. Aldehyde has a C double bond O to an H, right? That's my aldehyde that I made. All I did was just change this part of it to the aldehyde functional group. If I oxidize it further, again, that's the only part of the molecule that's going to change. I'm still going to have 3 carbons. Now I'm going to change the functional group to a carboxylic acid. That looks like that. All right, so you have a 3 carbon carboxylic acid being produced. All right, so if we look at our options here, we end up making the aldehyde first, 3 carbon aldehyde, and then we end up making the carboxylic acid second in that process. Okay, let's take a look at another one. It says give the primary product for the reaction of 2-propanol when it undergoes oxidation and dehydration. So first of all, let's draw this 2-propanol. So propanol would mean 3 carbons, 1, 2, 3, and it's an alcohol. It's got an OH attached to it on carbon 2. So that's 2-propanol. We're going to first of all oxidize it. All right, so let's see, that was A. We're going to oxidize it. Okay, so what type of alcohol is this? Is it primary, secondary, tertiary? Well, let's take a look. This is the carbon attached to the OH. This carbon is itself attached to 2 other carbons. That makes it a secondary alcohol. All right, when you oxidize a secondary alcohol, you should get a ketone. And all we need to do is to change the alcohol to a carbonyl. And that's it. For B, we're going to dehydrate it. All right, so we have here our alcohol, and we're going to dehydrate it. So that typically means we need an acid catalyst and we need heat in order for this to happen. Dehydrating means we're going to remove water in the form of H and OH, right? So we know right away where that OH is going to be lost from. It's going to be lost from that carbon. And we're going to lose an H from an adjacent carbon, right? And wherever we lose that H from, we're going to replace it with a double bond between those two carbons. So I'm going to still have my 3-carbon chain. That's not going to change. I'm just taking away now that OH and an H from an adjacent carbon. So let's say if I chose losing the H from the carbon on the right side, I now have to introduce a double bond on the right side there between the middle carbon and the carbon on the right. So we end up making the corresponding alkene, right? When you dehydrate an alcohol, you end up making the alkene. All right, and then the last one, learn in check 4, write the structure and name of the organic product when each is mixed with Tollens reagent. All right, so let's take a look at butanal. So butanal, 4-carbon aldehyde, 1, 2, 3, 4. The aldehyde group at the end. All right, so Tollens reagent is the Ag plus reagent, the silver mirror test. All right, and again, that is you're able to get a positive test if you have an aldehyde present. And what that does is it oxidizes the aldehyde group. So this here is going to be oxidized to a carboxylic acid. We're still going to have 1, 2, 3, 4 carbons. 1, 2, 3, 4. We're simply going to change that aldehyde to the corresponding carboxylic acid. Acetaldehyde is the common name for ethanol, which is a 2-carbon aldehyde, 1, 2. And there's our aldehyde functional group. Right, we have the same conditions, our Tollens reagent, Ag plus. Right, that will oxidize the aldehyde to the corresponding carboxylic acid. All right, and then we have the third one here, ethyl methyl ketone. Well, that tells you it's a ketone. So we have a C double bond O. We have an ethyl group on one side and a methyl group on the other. So methyl, 1 carbon, ethyl, 2 carbons on the other side. All right, if we subject this to the Tollens reagent, we wouldn't expect anything to happen, because if you remember the Tollens reagent, let's go back here really quick. The Tollens test or the Tollens reagent oxidizes aldehydes, but not ketones, right? So we're not going to see that silver mirror if we use a ketone with the Tollens reagent, right? So we're not going to see a reaction in this case. All right, the concept map here at the end of the chapter is actually a really good summary of the reactions of the alcohols, the aldehydes, the ketones, and the thiols can undergo. So I would encourage you to kind of use that as a review or as a study tool as you review chapter 12.